Okay, so good afternoon to all. I'm really excited to be here in FME conference. Since I started to work with this software, my daily work has become more easier, to be honest. So I'm really happy to be here and to present you here one of our major phases to calculating the coastal cut, and to do that we need to jump in this step that is calculating river width. But so let me just give you some introduction. I'm from city of Lisbon in Portugal. Okay, so we have a group of here working there. We are GIS data engineers. And yeah, here it's a global company, but has some pilot office around Europe. So in Lisbon we have one. Some nice pictures from Lisbon. I choose these particular ones because of the water. The water has a use, it's very important to a coastal country like Portugal. And as you have already heard in the morning, our travels, our discoveries, but yeah, the water has a really important dynamic in our country and the coastal cut, so that's why I choose these ones. So I'll be glad you can visit us in Lisbon. So I traveled this far to city of Vancouver, Canada, and yeah, really exciting to be here today. Okay, so I'm not going to pass too much time here about here, because today it's about FME. But just to give some introduction, who doesn't know here maps. So we have been here for a while, since 18th. We have been starting to make maps for cars, for routings. So our customers want to know to go to point A to point B, how can they get there? How can they get the faster route? But in our days, it's more complex than that. So our customers just don't want to know the faster route. They want to know actually how can my autonomous car choose the safely route? Where is my package? So we have been engaged with more complex questions from our customers. So we have been increased our database, and we have now this location platform where we have been just ingest more data and also different kind of capacities to align with the interests of our customers and answer all these complex questions. Okay. So, here maps, it's not all about maps. We do this, the group that I belong do these different maps. They are maps, but they are not navigation maps. So I'm part of GIS data engineer group. And most of the products that we do in Lisbon, it's postal code boundaries and census boundaries. So we play a lot with geometry. And most of our products are for business intelligence search. So most of our, so this is enterprise group. We do some content for internal, but also for external, like FedEx, Esri, so other customers. So this is an example here of the postal code boundaries. This is Portugal. We use FME. We have our database stored in PostGIS database, and we just built this geometry based on the nav streets product that we have from the streets, from the links, and other source. So we use also our internal API geocoder, also to geocode the address and be able to build this. So yes, you can see here, when we look at these polygons, each polygon has a value of a postal code. But when we look at it, it's kind of complex and ugly. It's not like a boundary as municipalities, you know, like really nice. So we try to see this and try to make our products a little bit more attractive. When we zoom into a specific municipality, we kind of lost track where we are, to be honest. So what is missing here in our products? It's the water representation. And we want to, you know, ingest this kind of data in order to our maps become more attractive. And also, when people are analyzing them, they could, oh, I'm not looking at a polygon that has water, right? So we want to make up an automatic process in the worldwide. So in our in the nations, so taking account all the countries, and pick up the water features that really has some representations, and like you see the other one with the cross that do not have it. So we want to come up something cleaner. And at the end, we have this representation. So the story here is that in North of America, and comparing North America with Europe, we have the size of the rivers could be, you know, of course, different. But what is big in one country, big in one country is even bigger than the other country. So sometimes by selecting only the size, it's not enough. Okay, and we want to be able to build a coastal cut with the oceans, of course, but also select in automatic way, an effective way, and a faster way, the rivers that touch the oceans that are really important. And we don't have the local knowledge for each country, right? So here the step is, here the goal is to have a dynamic process, a scalable process, and a faster process. And FME could, you know, help us to build this process that we have had in our minds. So the thing is what to represent. I don't want to pass here too much time what is a coastal cut definition, but here, this step, this is one of the phases of the coastal cut definition in our products is, okay, what should I represent? The first step is, okay, let me select the rivers that are really important and the others that I want to discard. And here is where it comes in, it's where we need to calculate the width of the rivers to discard the ones that we don't want and keep the good ones for our products. So just to give you here an example of Portugal, we have this data only in Portugal, so you can imagine in a worldwide. And yeah, we start. Okay, so let's start to measuring the width. Let's start to keep the really important rivers and discard the small ones, the smallest ones. So here is a bridge in Lisbon. It's not the Golden Gate in San Francisco, but very similar, right? His cousin. So what brought us here? How to measure river width worldwide. It's kind of looks good to go to the field and pick up some tape and measure. This is impossible, even if we could have fun for one day. So how can I apply this, taking account more than 4 million features? Because our database is really big. Then we start to think, okay, what do you know so far from our little place with geometry? We know that we have typical measurements, so area, perimeter. We can actually start thinking, measure the distance between the vertex of the polygons. You can try that, but we have a problem. We have over than almost 300 million vertices, and it's kind of complex to process this data in one time. So the goal here is that each team that is even working in Canada, Europe, it doesn't matter what country the team is working and is building the polygons, they want to have available on our database the coastal cut already defined, because our products will be all aligned. So it's very important to have a good coastal cut definition in the worldwide. Don't have a specific one for Canada, a specific one for USA, doesn't make sense, right? So our solution has to be dynamic and scalable to work in different types of coastlines. We don't want to use the attributes. We don't want, because due to the amount of source we have, we could have some descriptors from different from each country. So we don't want to use that. We just want to be focused on the geometry and could work with big data sets. Okay, so this is my workspace that it's not readable. This is the phase that we calculate the river width. Then we have another workspace, but it's just to validating this output. And this is the team from Lisbon. These fantastic guys. So let me go through these phases of the river width and explain a little bit the workspace. Okay. So this is the easiest part. We select all the oceans because the oceans are the feature that mandatory should be there. So this is the easiest part. Then we select the bays and the rivers that touch the oceans, and we could have a lot of data that touch the oceans. Then what we decided to do was build this oriented building blocks around our features, as you can see here. And the next step, and where is the magic also of FME, is to select the right side of the right side of the bounding box. Which side should I select? So the next phase is, so we divided this oriented bounding box in 10, and we generate this vertex, selecting the right side, and then just connect them. So we generate these cross sections, and afterwards we'll be calculating some statistics for these cross sections, but the ones that intersect the river. So we start to measure. And with this measure and the combination of these statistics, we can calculate the variance of the river. So if the variance is very small, as you can see on this image, we will discard them. And here is just the output of Vancouver, where these rivers will be immediately discarded in a faster way. This is an example of Vancouver, but our process discard in the wild world. Okay. So I have to say that when we thought of this process, we had to test a lot in a worldwide, because sometimes the sample, it's not enough to align to achieve what we really want. And this process, it's faster. It runs less than a day. It's fantastic. And for people like me, journalists, just data engineers that don't do too much code, I have to say that FME really helps me. and the little box just make my daily work even better. So thank you, FME, for for bringing me to the little box already with the algorithm behind. Much easier. So attribute to keeper with this process. We achieve this automated process, just clicking on a button each quarter that we want to release the products. We just know that we have a date, it's scheduled, and we will run in one day. So with simple, and here I'm going to just highlight the magic that I believe we do here. So it's just generate river cross sections. So the transformer oriented bounding box, that's it. Overlay with the vector data and calculating statistics with it. And then we have this, I just put here a better picture with the scale of the tester that we have. Of course we have to select the variants that we want to discard, and these are the pink ones. The variants in the river, the water poly in the south has different colors, as you can see. So the pink ones are to discard. So thank you once more. Hope you enjoy it.
Thank you very much, Ine. So I would like to open this up for questions. Does anybody have a question?
Hi, Ines. How do you calculate which vertices the chalk bounding box should be connected to one another?
We split the bounding box in 10 parts.
Right, so you split the 10, so you now have 20 nodes. How do you know which ones should connect to form your cross section?
I have there a couple of transformers. I can show you.
That'd be lovely.
Yeah, I can show you that. Yeah.
I was a bit misled, to be honest, by the title of the presentation at first.
Okay.
Was why I was here. So your main goal was to remove rivers from an ocean data set, basically.
Not the ocean. So our database is split. We have features that are oceans, and then we have water polys that could be a lot of things. Could be lakes, could be rivers. So we have to select the ones that touch the oceans and discard the ones that do not touch.
No, because I was under the impression that you had linear data sets, centered lines for rivers, and you were generating polygons,
Oh.
river polygons. I was like, wow, I want to know how to do that. But you didn't do that, right?
No. We have already the data, and we just calculate the width of the polygon, but it's more complex than when you start to think about it, and play a little bit with the data. Because this kind of nav streets has a lot of definition and a lot of vertex that sometimes in a specific scale or specific products do not make any sense to have it. So, yep. Sorry.
I was wondering, I don't know how long you've been doing this calculations, but if you've been doing it for more than 2 or 3 years, I was wondering, did you see a lot of variance in the width of the rivers, as in this with time, they
So we have been starting work on this for a while. When I joined this group 3 years ago, there were some basic ideas, but in the last year, that's where we engage more time to do it. Other priorities. Customers want our products aligned. We never made a time analysis, but this is dynamic. So, and we are picking up data from nav streets, also one of our products. So if that product is also updated and aligned with the difference of the river size along the years, this will be reflecting. Oh. No. But really nice to meet you, Ricardo, George, and Trevor. It's over there. They spoke about you, and really nice to meet you. Oh, there's one. Oh, so many questions, please. So our features, some of them are splitted already, and that's was the easiest part. So we have like a measurement definition for splitting the biggest water features, and that we split in couple of times and create the bounding box, because it's impossible, because sometimes the river starts in one direction and ends in the other, so the flow it's different. So oh my god, more. Oh. Mhm. Mhm. Okay, so I don't know if I can answer you that question. I don't know if I'm the right person, but what we use in enterprise engineer is one of our products that is nav streets. So the people that do nav streets, they probably use a lot of source, image, automatic recognition. So we have this fantastic group in the other side that kind of products these products, and also this is nav streets also was built with a fantastic team that have been doing field data collection also, but for the water features, to be more precisely, we have realigning different kind of sources, satellite image. To be honest, I can't give you 100% my answer because I don't work with that product. Oh, I don't build that product. But I will be glad if we can speak later, maybe I can give you. No more? Or just one more? Okay, last one. We sell it. Maybe I'm not the right person to speak about it. I'm just the technical guide. But we sell this to external customers, geomarketing, insurance company. So yeah, it's that this. So thank you once more.
Thank you very much.
Thank you.
Thanks for your great presentation. Please feel free to catch up with Ines if anybody has more questions.